Reverse time migration is used to create image of subsurface layers. RTM is a computationally expensive method. To get timely results, one way to speed up RTM is to distribute computation on a cluster of nodes using MPI. To exploit threading within a node, OpenMP is used. Analyzing hybrid MPI plus OpenMP applications are difficult, and hence performance analysis tools are required. Tuning MPI plus OpenMP applications require understanding at multiple levels, such as how work is partitioned among nodes, how threading within a node is used, and how functional units within a code are getting utilized. Rice University's HPC toolkit support analysis at each of these levels. The second accompanying video gives an overview of HPC toolkit and also shows how to use it to collect performance data. HPC traceviewer visualization of a time step of the DRTM application is shown. The figure shows performance profile for two processes, each having 8 threads. X-axis shows time and Y-axis shows different processes and threads within them. Here, thread 0 shown in a different color is the main thread that forks other threads. Each time step starts with stencil computation of the halo regions. Then the halo regions are packed so that they can be sent to the neighbors. Communication is posted using non-blocking MPI calls so as to overlap communication with computation. Then stencil computation for non-halo regions are performed, and this phase is overlapped with communication. Once stencil computation is finished, each MPI process waits for the arrival of halo communication that was initiated prior to stencil computation. Finally, code unpacks data from halo exchanges and performs interpolation if necessary. Initial assessment of the DRTM application using HPC Viewer is shown. In the figure, HPC Viewer is displaying top 5 time-consuming functions. HPC Viewer visualization shows that only 37.8% of the total execution time is spent on stencil computation. Also, 32.7% of the execution time is spent in idle state. This implies that stencil computation takes only 1/3 of the execution time and wait also takes around the same time. Another important observation is that memcopies take around 7.4% of the execution time, which seems excessive. The overhead of memcopies are introduced by an abstraction layer that DRTM employs to support parallelization using different programming models such as OpenMP and CUDA. Unlike CUDA, OpenMP works on same address space and hence data can be directly used without copying into accelerator memory. Improving abstraction layer to copy pointers instead of array improved performance by around 10%. HPC viewer visualization after removal of additional memcopies is shown. We can see that memcopies have disappeared from the list, and after the optimization, memcopies take around 0.3% of the execution time. HPC traceviewer visualization of the stencil computation for non-halo regions after memcopy optimization is done is shown in the figure. We can see that one thread remains idle while others are performing stencil computation. This implies there is load imbalance. DRTM's stencil computation is tiled to improve cache reuse. The tiles are smaller towards the bottom and right edges. Static scheduling is used for parallelization, and therefore OpenMP computes equal partitions of iterations with no knowledge of the tile sizes. The difference in tile sizes caused cores assigned with a collection of smaller tiles to finish early. Changing the OpenMP scheduling strategy to dynamic reduced the imbalance as shown, and this helped to improve performance by around 5%. HPC traceviewer visualization showing multiple time steps of all 16 processes after removal of thread level load imbalance is shown. Here, Pink color denotes idleness after stencil computation, waiting for halo exchanges initiated prior to the stencil computation to finish. This wait caused us to question whether real overlap of computation and communication is indeed happening. Making use of asynchronous progress mode in the MPI did not help. To enable true overlap, we introduced a communication thread and channeled MPI activities through it. This helped to improve performance by 10%. HPC toolkit visualization after introduction of communication thread is shown. Here, green color represents wait. We can see that waiting is removed from the middle processes. The difference in idleness of middle and edge processes denote load imbalance at process level. After analysis of threading and inter-process interaction, we checked how functional units are being utilized. We introduced hardware counters around stencil computation to measure various characteristics such as cache miss and so on. This helped us to realize there is improvement opportunity by reducing cache miss. Stencil computation loop uses the order Y, Z, X, where X is the innermost loop. Our stencil involves more points in the XY plane than XZ plane. Hence, interchanging Y and Z loop help to reduce L1 and L2 cache miss and improve performance by around 5%. In summary, with the help of HPC toolkit and hardware performance counters, we were able to identify 4 optimizations which helped us to improve performance of DRTM by around 30%. Reducing overhead cost due to unnecessary abstractions helped us to improve performance by around 10%. Reducing thread level load imbalance helped to improve performance by around 5%. Real overlap of computation and communication helped to improve the performance by around 10% again. And finally, improving cache reuse helped to improve performance by around 5%, and thus in total obtaining a total improvement of around 30%.